Right now, artificial intelligence lives in the cloud. When you ask a modern AI to write code or analyze a document, your request travels to massive data centers, processes on external hardware, and comes back. For most daily tasks, that setup works, but it creates a strict dependency. Every time you submit a prompt, your data leaves your machine and enters someone else's infrastructure. This creates an immediate problem for professionals. An engineer evaluating vendor blueprints or a lawyer reviewing confidential contracts cannot upload those documents to public AI systems. Their internal policies explicitly forbid it. For these users, capability is useless without confidentiality. This has generated an immense, quiet demand for enterprise-grade AI that operates entirely offline. The historical barrier to running massive enterprise AI locally has always been a memory problem. Processing speeds were sufficient, but the hardware lacked the physical space to load the models. This diagram shows a standard PC motherboard layout. Notice how traditional systems divide their memory into two separate pools. You have the main system RAM for the central processor and a physically separate bank of VRAM dedicated to the graphics card. When you try to load a heavy AI model into this architecture, it constantly forces data to shuttle back and forth across that physical gap. The system eventually runs out of VRAM, chokes on the transfer, and the model simply fails to run. If a model cannot physically fit into the available memory, its computing speed is irrelevant. That physical space limit is what kept professional AI trapped in the cloud. While the rest of the industry focused on building larger server racks for data centers, AMD looked directly at the engineers and researchers stuck at their desks. Their solution arrived in a new architecture called Strix-Halo, deployed in Ryzen AI processors. It was engineered intentionally to break the memory bottleneck. This schematic visualizes their approach: unified memory. The central processor, graphics unit, and dedicated AI processor all share a single continuous memory pool. With this shared space, professionals can load enormous AI models directly into memory alongside heavy CAD software. AMD moved the target. They stopped focusing on maximizing compute per server rack and instead prioritized the capability of the individual desktop. NVIDIA noticed this move immediately. Seeing a lucrative market slipping away, they pivoted their tactical focus back toward the local workstation. They responded with new unified memory systems built on their Blackwell architecture. First came DGX Spark, geared toward Linux developers, followed by RTX Spark, aimed directly at Windows-based professionals. But NVIDIA holds an advantage that extends far beyond physical chips. For nearly 20 years, they have meticulously built and refined their CUDA software ecosystem. Because of that head start, almost every major AI framework and development tool is optimized for NVIDIA hardware first. Replicating that level of software maturity takes decades, and that remains NVIDIA's strongest weapon. That massive deployment of both new hardware and entrenched software proves NVIDIA views the private desktop market as a critical frontier they cannot afford to lose. AMD has remained quiet in the wake of NVIDIA's aggressive push. Their strategy relies on a future product roadmap that is already set in motion. Industry reports indicate an upcoming refresh known as Gorgon Halo, which is expected to push unified memory capacity even further, reaching up to 192 gigabytes on a single board. Following that is their true next-generation architecture, codenamed Medusa. It is slated to introduce new Zen 6 CPU cores and utilize LPDDR6 memory, which will dramatically increase data transfer speeds. The next phase of this rivalry is cleanly drawn. AMD is attempting to win through overwhelming hardware capacity, while NVIDIA relies on the deep roots of its software optimization. As these machines hit the market, users need to adjust their expectations. Running AI on a private desk will not match the speed of a massive cloud data center. This chart compares output rates. A cloud model often generates over 100 tokens per second. If you run a massive 30 billion parameter model locally, expect around 6 tokens per second. While cloud wins on raw speed, professionals prioritize a different metric: data security. For an engineer analyzing a proprietary schematic, an accurate, highly reasoned answer that stays entirely on their hard drive is worth more than a rapid response generated on a public server. This rivalry forced a rapid build-out of personal hardware, turning what used to be a cloud-only luxury into standard desktop infrastructure. As these two giants fight for market share, the professional at the desk gains the most. They finally have the infrastructure to harness powerful AI while maintaining absolute sovereignty over their data.